Dear students, today I am going to discuss about the topic interference of light. Light is a form of energy. Light exhibits so many phenomena like reflection, refraction, dispersion, total interreflection, etc. Along with this, light also exhibits the phenomena like interference, diffraction, polarization. In this unit or in this topic, we are going to discuss on one of the phenomena. It is interference of light. Before that, in optics there are two branches: geometrical optics and physical optics. In geometrical optics, the phenomena like reflection, refraction, polarization, etc. are explained by assuming rectilinear propagation for light. Light travels in a straight line, and by treating light as a ray, indicating by a straight line with an arrowhead, treating light as a ray, the phenomena like reflection, refraction, interreflection, dispersion, all these things are explained under geometrical optics. But this ray nature could not explain the phenomena like interference, diffraction and polarization. So one more branch was evolved in the field of physics, in the field of optics. It was wave optics. In this wave optics, wave nature is assumed for light by Christian Huygens. Huygens treated light as a wave, and in his wave theory, he explains that light travels in the form of a wave, and he considers the idea of wavefronts. A wavefront is nothing but the locus of all the points which are vibrating in phase. So according to Huygens' wave theory, light spreads out in the medium in the form of concentric circles of increasing radius known as the wavefronts. Using this wave nature, he explained the interference of light. What is interference? See, light is treated as an electromagnetic wave. It is a simple harmonic wave. It is represented by the equation E vector equal to E sin omega t. Here E is the amplitude of the wave, omega angular frequency or angular velocity, and you know the relation between angular velocity and angular frequency. Omega is given by 2 pi f, where f is the frequency. Omega also defined as 2 pi by t, the t period of that wave. So here E vector equal to E sin omega t indicates that light is a vector, indicated by the letter E means it's an electric vector. So light is an electromagnetic wave. What's an electromagnetic wave? It is a combination of, or it is a wave produced due to the vibrations of electric vector and magnetic vector at right angles to each other. The vibrations gives rise to the displacement of the wave, denoted by E equal to E sin omega t. Since all the properties of light are mainly due to electric vector, light is represented by the equation E vector equal to E sin omega t. So light is an electric vector. Now interference. Interference means it is the modification in the intensity of light due to superposition of two waves. Due to the superposition of two waves. Whenever two waves they fall on each other, there will be modification in the intensity. That is called as interference of light. Modification means light intensity becomes maximum and minimum alternately. It is called interference. Now let us consider two waves having displacements E1 vector equal to E1 sin omega t and E2 vector equal to E2 sin omega t plus phi. Here the difference between these two waves, the second one is having an extra phase phi. Phi, the phase difference between these two waves. E1, E2 are the amplitudes of these two waves. Suppose the two light waves superpose on each other, then a resultant wave is produced having displacement E1 vector plus E2 vector, and when we analyze this, when we solve this, finally we get an expression in the form of sine wave again having amplitude R is equal to square root of E1 square plus E2 square plus 2 E1 E2 cos phi. That simplification is not included. Finally we get a single wave. After superposition, we get a single wave. That single wave is having amplitude given by this. And in case of a wave, the intensity of the wave is always varies direct as square of the amplitude. So I proportional to r square, where I is intensity of the wave. So that the intensity of the resultant wave is given by this equation. So whenever two waves they superpose on each other, a single wave, a resultant wave is produced with intensity given by this. Now intensity is the function of phi. Depends on the phase difference between the two waves. It's a function of phi. So that there will be variation in the intensity depending on cos phi. And I can be maximum only when cos phi can have the cos phi takes the maximum value. When cos phi is maximum, then I becomes maximum. When cos phi becomes minimum, then I becomes minimum. Let us consider the first case, intensity of the resultant wave maximum. When the intensity of the resultant wave becomes maximum, that interference is called as constructive interference. When the two waves superpose on each other, producing a resultant wave having maximum intensity, the interference is called constructive interference. So, for this to happen, for constructive interference to happen, cos phi should have the maximum value, and the possible maximum value for cos phi is +1. When cos phi is +1, then I becomes E1 square plus E2 square plus 2E1 E2. So that I is E1 plus E2 whole square. It's a maximum intensity. And cos phi equal to +1. This is possible only when phi takes the values 0, 2 pi, 4 pi, 6 pi and so on. Cos phi becomes +1 when phi takes the value 0, 2 pi, 4 pi and so on. Or in general, if phi is equal to 2n pi and even integral multiple of pi, when phi becomes an even integral multiple of pi for the values of n as 0, 1, 2, 3 and so on, in all such cases, for all those base values, the intensity of the resultant wave is maximum. This is called as constructive interference. The second one is, this is the modification. This is how that modification takes place there when the resultant wave is produced. And in the medium, when the wave travels through a medium, in the medium there are certain points wherein intensity is minimum. Intensity becoming minimum means the interference is called destructive interference. There the condition is intensity minimum means this I becomes minimum if cos phi is minimum. Cos phi minimum means the value is possible value is -1. When cos phi is -1, cos phi takes -1, intensity becomes minimum. That interference is called destructive interference. There phi values are pi, 3 pi, 5 pi and so on. For all these values of phi, cos phi takes the value -1, so that intensity becomes minimum. This is destructive interference. And these two are, see, this one and this. These are the conditions for constructive and destructive interferences. And here I have written one more condition, one more expression, that is for delta. Delta, this symbol indicates the path difference. The difference in path between those two waves. Now, we have the relationship between phase and path like this. Suppose you have a wave of wavelength lambda. Then, any two particles separated by a distance lambda, they differ in phase by 2 pi. So, lambda corresponds to phase difference 2 pi. So that any phase phi corresponds to any path delta, and we connect them by this relation. Phi is always 2 pi by lambda into delta. This is the relation between phase difference and path difference. So that path difference is lambda by 2 pi into phi. Using this, we get the condition for constructive interference in terms of path difference as delta equal to n lambda, where n takes the values, it's an integer 0, 1, 2, 3 and so on. Similarly, for destructive interference, the condition in terms of path difference between the waves, it is 2n plus 1 lambda by 2, and odd multiple of lambda by 2, here also n, an integer takes the value 0, 1, 2, 3 and so on. And this is about the two types of interference, constructive interference and destructive interference. This is how modification in the intensity of light takes place when the two waves superpose on each other, to produce a resultant wave, a single wave. And when this modification takes place or in interference, a pattern is always produced on a screen, and that pattern always consists of alternately bright and dark bands or bright and dark fringes. We call them as fringes also. Alternate bright and dark fringes are seen on the screen placed in the path of the superposed waves. And this is about constructive and destructive interference. Now, to produce a sustained interference pattern, sustained means a continuous one without any interruption. To produce a sustained interference pattern, we need two sources. And the sources, they should be coherent. They should satisfy the condition called coherence. Coherence means those two waves, they should send, they should emit the light waves of same frequency, same wavelength, equal amplitude or nearly equal amplitude, and the important one is there should be a constant phase difference between those two waves. When two sources, they send out or they emit light waves satisfying these conditions, then only those two sources, they behave like coherent sources. So to produce sustained interference pattern, we should have coherent sources. What is coherence? The sources should emit light waves of same frequency, same wavelength, equal or nearly equal amplitude, and they should have a constant phase difference between the waves. Then only their sources, they become the coherent sources. So, is it possible to get a sustained interference pattern using two identical independent sources? Do they behave like coherent sources? Two identical sources, do they behave like coherent sources? No. Two identical sources, they do not, different sources, they do not behave like coherent sources. Even though they emit light waves of same frequency, wavelength, equal amplitude, etc., still the waves, they may not have constant phase difference between them. There may be abrupt change in the phase difference between those two waves, so that two identical independent sources, they do not behave like coherent sources. So, in order to get coherent sources, there are certain methods to derive the coherent sources from a single source. And the sustained interference pattern is produced by coherent sources. The sources should be coherent one condition and other things. And these coherent sources, they satisfy all the required conditions to produce the sustained interference pattern. And this is about the interference. And whenever an interference pattern is produced on the screen, we see alternate bright and dark bands on the screen. So here, to produce the pattern, for the first time, this interference phenomena was demonstrated by Thomas N using his double slit experiment. The experimental setup was consisting of a single source, a monochromatic source. You know what a monochromatic source is? A monochromatic source is one which sends out light waves of single wavelength or single color. In that experiment, he used a single slit illuminated by a monochromatic source of light. Then he placed two more slits separated by opaque space, and he kept one screen, and on the screen he observed the interference pattern consisting of alternately bright and dark bands. So this was the setup, a slit illuminated by monochromatic source of light and two more slits separated by identical slits having same slit width. Then one more screen we place. Let capital D be the separation between the source and the screen. Let S1, S2 be the two slits illuminated by the same source, so that these two behave like the coherent sources. The two slits separated by the opaque space illuminated by the same source, so these two, they behave like the coherent sources. Pattern is observed on the screen. At the center, always a bright fringe is produced. On either side, above O and as well as below, alternately bright and dark fringes are produced on the screen. Now, let small d be the separation between these two slits. Let small d separation between the two slits. Capital D distance between the it is the distance between the slits and these two slits and the screen. Lambda, the wavelength of the light used to illuminate the slits S1, S2, so that the fringe width is given by the formula beta is equal to lambda d divided by small d. This is the expression for fringe width. The symbol beta represents fringe width. Fringe width means the distance between any two successive bright fringes or any two successive dark fringes. Beta, distance between any two successive bright fringes or any two successive dark fringes, that is known as the fringe width, given by the formula lambda d by small d, capital D, distance between the slits and the screen, small d, separation between the slits. This is the expression for the fringe width. This was the experiment done by Thomasian using double slit. So, double slit, one of the methods to produce the coherent sources. See here, using this double slit, these two slits, the double slit setup, coherent sources are produced. S1, S2 behave like the coherent sources. And here, the coherent source is produced by one method called as division of wavefront. See, there are two methods to produce a coherent source. The two methods are division of wavefront and division of amplitude. These are the two methods by which one can derive the coherent sources. See, as I told, two identical independent sources, they may not behave like the coherent sources. So, one has to derive the coherent sources from a single source. The two methods are division of wavefront and division of amplitude. This the double slit is an example for deriving coherent sources by the method of division of wavefront. See here, in this method, a wavefront is divided into two equal parts. A wavefront. What actually a wavefront is? A wavefront, so suppose if you have a source of light, it sends out light in all directions. According to wave theory, light spreads out in the form of concentric circles of increasing radius, and the locus of all the points vibrating in phase is called as a wavefront. See, this is the wavefront. This one is the second wavefront. So, light spreads out in the form of the waves, or it's called as the wavefront. So, here, in the method of division of wavefront, the incident wavefront is divided into two equal parts, then interference is produced. One more example for producing coherent sources by the method called division of wavefront is using Byprism. See, I have written the figure here, diagram of this is called the Byprism. Byprism is a device which can produce two coherent sources by the method of division of wavefront. What is Byprism? Let us see later. So, in the method called division of wavefront, either using double slit or using Byprism, one can derive coherent sources. The second method is division of amplitude. In this method, the amplitude of the wave is divided into two equal parts by partial reflection and partial refraction. The amplitude of the wave is divided into two equal parts by partial reflection and partial refraction. And the example for this is Newton's rings and air wedge. Air wedge means, see, when very thin air film is formed between the two glass plates in the form of a wedge. A wedge-shaped air film is formed between the two glass plates and it's illuminated by monochromatic light. There, by partial reflection and refraction, two coherent sources are produced. So thus, these two are the methods to produce the coherent sources. Now, let us see how a Byprism is used to produce two coherent sources by dividing wavefront into two equal parts. Byprism, as the name says, it is the combination of two prisms placed base to base. Very thin prisms placed base to base to form a single prism. Actually, after the combination, it becomes a very thin prism, very thin. This is the representation of a prism having two acute angles and one obtuse. This one obtuse angle is 179 degree, the other two angles are half degree each. This a biprism is produced using two prisms by keeping them base to base. This is a biprism. And the biprism produces coherent sources by adopting the method called division of wavefront. Already written the diagram here. So this is a biprism. A slit is illuminated by monochromatic source. Now you see, these two are the two rays which are very close to the principal axis, or this line. These are very close, and these two, I have considered totally 4 rays. If you consider these 2 rays, and in the prism always after refraction, the ray bends towards the base. If you consider this ray, it's the incident ray, always it bends towards the base, it moves like this and falls on the screen. Similarly, one more ray bends up like this, and 2 more extreme rays. As a result, an interference pattern is produced here. And here say how the coherent source are produced is. See these, the refracted rays, when we produce them backward, we get one source, one virtual image. So S1 is produced here and one more here. So S1, S2 are the virtual images of S produced after refraction through this biprism. S1, S2 are the virtual images of the slit S. And these two virtual images, they behave like the coherent sources to produce the interference pattern on the screen. A pattern is observed in this region on the screen, consisting of alternate bright and dark fringes when the slit S is illuminated by monochromatic source. See here, after refraction, if you produce the refracted rays backward, they meet each other at S1 and S2, and S1 and S2 are the virtual sources behaving like the coherent. This is how, by the method called division of wavefront, two sources are derived, which behave like coherent. This is how a biprism produces the coherent sources. And this biprism is usually used to determine the wavelength of light. If you have a monochromatic source of light whose wavelength is not known, then using biprism, by deriving the virtual sources, and one can measure, or one can calculate, or one can find out the wavelength of that unknown wavelength of that monochromatic source of light. Here, the experiment consists of, see what we do is, in the experiment, we use a biprism and we keep it on the device called optical bench. We need an optical bench. A very long metallic table provided with uprights or the holders to hold biprism and other things, eyepiece, etc. So using that optical bench and the biprism, we can measure or we can calculate the wavelength of the light emitted by a source. So this experiment consists of 2 parts. One is measurement of the fringe width. Second one is measuring the distance between the sources S1 and S2. First part, using the biprism. See there, the optical bench or metallic bench provided with the uprights. There at one end we keep the slit. In one of the uprights, a slit is placed, slit is fixed, illuminated by monochromatic source. In another upright, the biprism, it is cleft. We keep the biprism in another upright, and in another upright, we keep an eyepiece provided with the micrometer. This is an eyepiece provided with the micrometer. Let D, the distance between the eyepiece and the slit S. Here, this biprism produces 2 virtual sources, S1 and S2, and these 2 virtual images, S1, S2, virtual images of S. And these 2 virtual images, S1, S2, behave like coherent sources so that a pattern is observed through this eyepiece. When we see in this eyepiece, an interference pattern. The eyepiece behaves like the screen, then the pattern is observed. Using the micrometer screw attached with the eyepiece, by rotating that, you can move the fringes and thereby you can take the readings also. By taking readings to the different number of fringes, fringe width can be calculated. That fringe width we usually denote it as beta is equal to beta is given by lambda d divided by small d. This is the relationship between fringe width, wavelength, capital D, small d. It is beta is lambda d by d. So here in this, using this setup, beta can be measured. Beta measured using the micrometer screw provided by the eyepiece. So what I will do is, by rotating the micrometer screw, we coincide the crossway to one of the fringes, either a bright or a dark. Then we take the reading, we move that micrometer screw again, we move by any number of fringes, say 2 or 3 or 4 like that. Again we take the reading. The difference between the two readings gives the width of either 3 fringes or 4 fringes. Using that we calculate width of one fringe. That is beta. So beta is measured. The second one remaining here is D, capital D. Where can be measured? The optical bench. It's provided with the meter scale. Using that itself, directly D can be measured. The remaining is small d. How small d can be measured? To measure things, S1, S2 are the virtual images. Directly we can't measure the distance between S1 and S2. Since S1 and S2 are the virtual images, directly D cannot be measured. So to measure D, there is a method. It is to measure D. To measure D, a convex lens is introduced between the eyepiece and the Byprism. We introduce a convex lens between the Byprism and the eyepiece. Here is the convex lens. It is introduced. And here the convex lens, the convex lens, it should have the focal length, a very long focal length. A convex lens of long focal length is taken, and first of all, we keep it very close to the Byprism. Keep the lens very close to Byprism and slowly move it. When you see through the eyepiece, at one position of this convex lens, say L1, at one position near to the Byprism, between the Byprism and the eyepiece, at one position in the field of view of the eyepiece, you can see the two images of the slits S1 and S2. The real images of the virtual images S1, S2. Real images are seen for one position of the lens, almost close to the Byprism. We see to enlarge, the images are enlarged. Very long lines separated by a little more distance are observed or seen, and we call it as the enlarged image. And using a micrometer, we measure the distance between these two images. Instead of the real images, the distance can be measured, it will be D1. This is enlarged image. And for this enlarged image, let U be the distance between the lens and the slits. Let V be the distance between the eyepiece and the lens. Usually the symbols U and V represent object distance and the image distance. So the distance are measured from the lens to the slit, object distance, lens to the image, eyepiece, it is the image distance. Let U and V be the object and image distances for the position L1 of the lens. Next, what we do is, we slowly move the lens towards the eyepiece, and at another position, again, as we move it, at another position, again, the two real images of the slits are seen in the field of view of the eyepiece. The two more images are seen, but the images are almost very close to each other, and very small lines are seen, and we call it as the diminished image. Again, for one more position, say, of the lens, say L2, we get the images of the slits S1, S2, which is the diminished image. very small lines separated by a small distance are observed. So we get the diminished image. Like D2 be the separation between the two images. It is measured using again the micrometer provided in the eyepiece. This is how we measure D1 and D2, which are the distances for the magnified, the size for the magnified image and that of the diminished image. And here, for the second position of the lens, what happens is the object and image distances, they get interchanged. Initially U was the object distance, and now the U becomes exactly equal to that of the image distance, and V becomes exactly equal to the object distance. And these two positions of the lens are called as the conjugate foci. When the focal length of the lens is very large, there is a shift method to determine the focal length of the lens. There, the object and image distances, they get interchanged. First position UV, for the second position U becomes equal to V, exactly equal to that of V, and V becomes exactly equal to that much of U. This is how object image distances are interchanged for the second position. Let them be V and U. And in case of a lens, we always define magnification. And magnification defined as the ratio of object distance to image distance, as well as it's also given by image size, ratio of image size to object size. Magnification in case of a lens defined as ratio of image distance to object distance, also defined as image size to object size. In the first, say, the lens is the same, so in both the cases, magnification remains the same. For the first case, magnification, first position of the lens, L1, magnification is V by U. There the image size is nothing but separation between the images. We took it as D1. Object size nothing but the actual separation between the virtual images. It is D. Thus we have M as V by U, also given by D1 by D. And for the second position of the lens, the same magnification we define as object image size to, image distance to object distance, but there the image distance is U, object distance is V, also given by image size, it is taken as D2 diminished one by D. This is 2. By U by V, it is D2 by D. So using 1 and 2, by multiplying, equations 1 and 2. See, if you multiply left hand side, V by U into U by V is 1. So that we get 1 is equal to D1 D2 by D into D square. That implies D square D1 D2, D is square root of D1 D2. This is how the distance between the virtual sources S1 S2 is calculated by measuring the values of D1 and D2. Now beta is lambda D by D, so that lambda is beta D by D. So therefore lambda is beta into root D1 D2 by D. Here beta is measured, D1 D2 are measured, this is also measured. This is how the unknown wavelength lambda is calculated using the Byprism. So in this Byprism experiment, using a Byprism, keeping it on the optical bench and all, we measure the unknown wavelength lambda. Students, with this, I stop here. Let us continue the next class with the next topic. Thank you.